on episode number 24. And I'm answering the question today, why do ultrasonic transducers have a preload? So, by preload, what I'm referring to is the main direction of mechanical oscillation or vibration of your specific transducer type, whether that be bolt Langevin transducers or whether they be also just a, epoxied piezo onto another structure and you can basically assemble using epoxy or another type of adhesion method. In both of those cases, there is preload, which is applied in different cases. For the epoxy material, many times we're depending on thermal expansion, like you cure your epoxy at a higher temperature. When you get back to room temperature, the metal contracts more, squeezing the piezo. And in the bolt clamped Langevin transducer, it's a little bit more obvious where you have your bolt and you tighten it in order to achieve a certain clamping force onto your piezoelectric ceramics. So why do we do that? What's the purpose? And what are in this topic, I'm going to be speaking kind of briefly on just why we do it. In the coming episodes, I'll discuss a little more details about their analysis and determining that. I might get into FEA a little bit because it is actually quite important for the understanding. It's not something. It is something you can do just by doing tests on the bench, going back and forth, iterating. But you'd also like to understand if you have a optimized geometry for most effectively applying preload, because you can't apply it ineffectively. That's going to cause you to provide a lot more preload and get a lot less out of it. So let's continue. So we're answering, why do ultrasonic transducers have a preload? Compressive bias, you could say, compressive stress bias. The first is to keep the transducer together. Now, this is especially true in a bolt clamped transducer, where you do sometimes have epoxy, but it's not But the primary purpose of the epoxy is not to keep the transducer together. Rather, the actual bolt clamp mechanism is doing that. So this prevents gapping. It prevents the crystals or the other components from actually leaving contact, because you always want to have contact to ensure optimum acoustic transfer. Once you start losing contact, you run into a whole mess of nonlinearities. Your resonant frequencies now suddenly change because you don't have good acoustic contact between the parts. So that also causes issue. That would definitely cause issues. And if you just have epoxy there, it's still not going to provide the same stiffness as having those two components actually really firmly pressed together. And the next one here is slipping. So what it can also cause is, if you do have this gapping or sort of a little bit of separation between the components, the crystals or the other components can actually slip, because although you have bolt clamped, the threaded portion of this of the clamping mechanism is only perhaps, for example, on the back mass and on the horn, or it's perhaps a bolt which doesn't necessarily thread onto the back mass, but the threaded part is on the horn, for example. And in that case, you may have slippage in between the other components, like the crystals or other passive kind of mass or elastic components you have in that train, including the back mass. So you can have slippage, which is going to really reduce the efficiency and the performance of your device, and it's going to make it seem quite unusable. The second is to keep the crystals under compression. So piezoelectric crystals are ceramic materials. They are poor under tension, so they can only withstand a small amount of tension, but they can withstand a lot of compression. So by adding a compressive preload to your piezos, you are actually allowing them to operate in a completely compressive mode. So, for example, let's say this was the zero mark for stress. Then you had a bias compressive. So this would be tension. You had a bias compression, and then you have oscillation back and forth, like your level of stress or goes up and down. Now you're still seeing 100% compression, which is the ideal format, versus if you started off at a zero stress condition, you would now be operating in tension and compression. Your fatigue would happen much faster. You'd be much more susceptible to cracking as well. So keeping your crystals under compression to the extent possible. Now, these are rules of thumb. They're not they are not. There are many unique situations where you'll perfectly be fine without putting a lot of compression or kind of following these rules of thumbs to a T. But this does provide a general framework for you to start to understand, what the purpose of some of these mechanisms of adding preload is. So we got to keep the crystals under compression in order to stop them from cracking, and also extend in order to stop them from cracking and be able to have a longer life. The next part, and all these are related, so I'm kind of jumping back and forth here, but I'm making this three distinct points just for us to remember. So the next is extend the useful operation range. So I mentioned that we had this baseline zero stress, and we had this compressive bias. Now we can actually operate to a much larger amplitude than we would have been normally able to achieve. So if you were, let's say, to operate at a zero stress or zero compressive bias, we would only be able to, let's say, achieve this much tension. Drawing this much, you got to be a little bit creative and imaginative now. So you'll only be able to achieve this much tension before fracture or before a very low life expectancy. But if you biased it, you could actually achieve a lot more. You can go up to the tension point slightly. You'd actually able to achieve a lot more power into a transducer, which then makes it much more useful. You may have to use less transducers. You may be able to get away with less piezo material in your transducer. So it basically extends that useful range, how much power you can input. So it makes it a higher power transducer. The easiest way to make your the easiest way to make your transducer higher power, being able to withstand larger levels of oscillation, is to increase the level of preload. But you have to do that within reason, though. So let's just go over the three again. The first, we got to keep everything together. That's why we have preload. Just simply just the mechanical part of it. We want things together, and this actually will reduce the occurrence of gapping and slippage, which do ruin the device performance. Also, we keep the crystals under compression so they have a longer life, and also we extend the useful range. The amount of power you can input, the amount of mechanical oscillation you can have from your crystals into your structure. You can also improve that by optimizing or having and optimizing your preload amount. You've been watching the Piezo SHOCK Show hosted by yours truly, Dr. Shakani. Please check the description for links on the presentation notes from today. Also, to sign up for daily updates on these videos when they're released, you'll also get the notes directly in your email. And you can also check out my consulting offerings and services. There are a couple of new things I put on there, so feel free to go on my website and take a look around. Thanks for watching, and I'll see you in episode 25 tomorrow. See you then.